Okay, this video gives you a quick and brief introduction into the Riemann integration theory. Just as a revision, I will give you the criterion for Riemann integration, and I'll show you on a few examples how this works. So we discuss with you Riemann integration. Generally, this means that you look at a function, define a segment AB, and that's a typical example. To construct the concept of Riemann integration, you have to first partition your interval into smaller subintervals with some set of points. Like, for instance, here's the sine function, and I partition it. Let's say example of this partition. Here it is. Here it is. So that would be the point. This would be the point x0. That's the point x1. The one next to the last one, xn take 1, and the very last one is xn. Now, what you do next, you introduce increments, the smaller intervals, the lengths of the smaller intervals. On this picture, by the way, I chose the points uniformly distributed. It's not generally the case. You're free to choose any partition you want, but just for the convenience and for the beauty of the picture, I just made them uniformly distributed. Now, to measure how small the partition is, you introduce this quantity, which is a max of all of these smaller lengths, and you call this diameter of your partition. And now you say that the integral of your function over the interval AB, and that's the symbol which stands for this integral, will be the limit of this slope. It will be a limit where you choose some point psi, and you choose this point somewhere within this smaller k interval. You take the value of the function at this point, and you multiply by the length of the underlying smaller interval, and you sum everything up. Geometrically, this is the area of this type. Well, I showed you a few choices. For instance, for this smaller interval, if I choose the psi function coinciding with this left point, then this one element of my summation will be the area of this rectangle. If I choose my point for the same interval like this, if I choose this as the psi point, then the interval will be this lighter blue rectangle. This not the integral, but the one summed of my summation. Again, you're free to choose any point, not specifically left or right point of your smaller subinterval. You can choose the point inside if you want. And the limit of the sum, given that this limit exists, will be your Riemann integral. Of course, the main question is when this limit exists. And in fact, the Riemann integration theory requires that this limit does not depend on the choice of a partition or the choice of these inner psi points. And the criterion, which ensures that the function is truly Riemann integrable, so that the function has this limit, the criterion goes like this. In order to give you a criterion, I have to introduce two extra concepts. I have to introduce the minimal value of my function over this kth smaller subinterval, and the maximal value of my function over this smaller subinterval. Now, having these two particular values, little m and capital M, I can introduce a sum like this, where the value of the function is replaced by the minimal or maximal values. One of them normally is denoted by S substar, and the other one is S superstar. This is called the lower integral sum. This is the upper integral sum, and the criterion for the integration says that the function f is integrable over the segment R, AB, should be AB in brackets. The function f is integrable, and that's a symbol which stands for the class of Riemann integrable functions over the segment AB. It is integrable when both limits exist and identical to each other. That's the first criterion. There is another one, which says, in fact, you can even, there's another one, development of this criterion, which more useful for the practical purposes, which says this: if you introduce another number, omega k, which is the difference of the max value and the mean value over the kth subinterval, and the name for this value, in fact, the oscillation of the function over the kth interval, then this limit, look at this, the limit of the oscillations times the length of the underlying subintervals, and sum, the limit of such a sum must be 0 as soon as the diameter of your partition goes to 0. This is a basic criterion for testing Riemann integrability in practical examples. Yes. Okay, I'll show you a quick example where this criterion is. I'll show you a few examples where this criterion, in fact, will be used. The easiest one is, of course, this statement, which I call lemma. This statement, which I call lemma, and the statement says that the continuous functions over segment AB. In fact, let me just fix this. It should be segment AB, and it should be segment. Continuous functions, remember this symbol. If you don't know that, then now you know it. C bracket AB means the class of all continuous functions over the closed interval AB. They always Riemann integrable over the interval AB. So this symbol, it means subset, so every function which belongs here will always belong here as well. I'll show you a quick proof. Basically, all the information we need comes from the fact that if the function is continuous over a closed bounded interval, it is also uniformly continuous. And uniform continuity, it's something which I expect you to remember. It goes like this. For every positive epsilon, you can find a delta, which is positive, such that, so if your function f came from CAB, if your function f came from CAB, then that's something which you can expect. Let me put it here. For the function f which came from CAB, it's a function which is continuous on a closed bounded interval. For every epsilon, you can produce a delta, such that as long as x and y less than delta, the value of the functions in these points, x and y, the difference of the values of the function at these points is less than epsilon. Of course, x and y here from AB, from the interval, from the segment AB. Right, so this observation, this is a consequence of the fact that my function is continuous. And this observation is enough to establish this thing. Indeed. If I fix now epsilon, positive epsilon, if I now choose a delta, like this, for such epsilon, look what happens. I choose a partition with the sole condition that this partition has a diameter less than this pre-chosen delta. Delta chosen with the help of the continuity or uniform continuity property. If I have such a partition, which means that every single individual interval here will be less than delta in length, then well, that's what it said here, every single interval will be less than that, but which is more interesting is that the oscillation of my function over such subinterval, because its length is less than delta, oscillation will be less than epsilon. And now all we have to do, we have to just estimate this sum carefully. So all we have to do now, we have to carefully estimate this sum, which appears in the criterion of integration, and that's my estimate. I look at the sum, and I estimate the sum in the following way. First, each oscillation is less than epsilon, so I just replace it with the bigger value, epsilon. The remaining part is just sum of the lengths of the smaller intervals, but this sum obviously returns the length of the bigger interval, and we end up like this. And that basically finishes the proof, because look at this, for every fixed epsilon, I found a delta such that as long as the diameter of my partition is less than this delta, my sum less than, well, a little bit scaled epsilon. This is exactly the definition of a limit, which ensures this. That's why every continuous function is Riemann integrable. Now, I'll give you one example of the function which is not Riemann integrable. Example. That will be the function which is defined like this. Look at this. It's a function which takes value 1 when x is a rational number, and that's the one which takes value -1 when x is irrational number. Or in fact, I'll take the value 0 here for changing. Let me just change it a little bit. I'll make it 0 rather than -1, because if I do that, then this function, it is a well-known Dirichlet function, and that's one of the examples of the functions which is in fact not Riemann integrable. Again, this can be tested via this criterion. Look at this. If I look at this function, then first I have to compute the mean and max of my function over subintervals, and that's actually, for this function, it's easy. Whatever the partition is, no matter which partition I choose, my mean will always be on, in fact, 0, because I changed it to 0. My max will be 1, because no matter how small the interval is, there will always be a rational point inside this interval, and so there will be a point where a function takes value 1. So my oscillation of a function is always 1, which means that if I compute this sum, oscillation is 1, so we end up with the sum of the smaller subintervals. We know this sum is just the length of the big interval of integration, and we end up with this. Obviously, this will never go to 0, no matter how hard you push your partition, the diameter of your partition to 0, which means that this Dirichlet function is not integrable. Interesting point about the Dirichlet function, or in fact, the example of Dirichlet point, the example of the Dirichlet function gives you this understanding why Riemann integration is so uncomfortable to deal with, in fact, so inconvenient to deal with. Actually, to make this demonstration, let me just do it like this. I'll take this Dirichlet function and I'll just modify it a little bit. That's the function. Let me just do it like this. I'll just move it left a little bit. Let me make a copy of this function, and now let me just change it to the way it was originally, -1. Look at this function. In order to explain this to you, actually, I'll call to your memories. I hope you studied this in your previous topics of series of the series, number series, and the way we test the number series for convergence. But if you did that, you probably remember that one of the main tools there is what is called the comparison principle. It says that if you have two series, like this one of them, for instance, AK, and the other one is, let me just put it completely, 1 to infinity, BK. We put here the limits of summation too, just to make it more precise. Okay, 1 to infinity. If I have two series like this, the comparison principle, when you studied series of numbers, said to you that if you know that the absolute value of the AK is controlled by the BK, then the convergence of this series you can imply the convergence of this series with the convergence of this series. That's in basic terms what the comparison principle is. This is something which is not true, and something which doesn't have any analogous statement for the Riemann integration, and the example of this function makes it very clear. Obviously, this is the very minor change over the canonical Dirichlet function. For this new function, which has -1 here, You can also repeat the same sort of argument. The only difference will be here will be -1 rather than 0, and here will be 2 rather than 1. So this function, like the original derivative function, will also be not Riemann integrable. However, if you look at this function and if you think of the absolute value of this function, it is just constant 1, which means that this function, just make it, is in fact Riemann integrable. Is in fact Riemann integrable. This function. So the original function is not Riemann integrable. Let me put it here. No matter which interval that is. The original function is not Riemann integrable, but the absolute value of that function is Riemann integrable, which means that actually nothing similar to this exists for Riemann integration, and that's really bad, because if you did fair share of number series analysis, you probably realize by now that this comparison principle is very, very useful. It makes your life really, really easy there. And there isn't anything like that for Riemann integration. Yeah, well, there's another, on this slide I have another little piece of a demonstration why the Riemann integration is so inconvenient for many tasks in analysis, and that's the one which actually goes about limits. Again, if you look at this Dirichlet function, or if you look at this Dirichlet function, I can make the following another adjustment to this function. I can introduce a special set Q sub n, which will be rational numbers, not all of them, but only those P on Q numbers with the property that, well, this is all like a standard things. P is integer and Q is positive integer. They are co-prime, but that's the extra thing which makes it Q sub n. So we just take only those fractions whose denominator doesn't exceed n. For instance, Q1 will be just z. Q1 will be just z. Now, look at this, what I'm going to do. I'm going to consider now function f sub n, which will be 1 when x is from this special set Q sub n, and, well, -1, or in fact I'll change it in a sec, or 0 when it's from the rest of the numbers. This function is Riemann integrable. For every n, in fact, the fn actually can be represented as a sum of the indicator functions of point sets, rational point sets, and where the rational point come from this Qn set, and this is a finite sum. In fact, I should say here 0, 1, then it is a finite sum. Each individual indicator function of a single point is in fact Riemann integrable, so the finite sum of Riemann integrable functions is Riemann integrable. So these Fn functions are Riemann integrable. Also, you can observe that actually your original Dirichlet function is a limit, pointwise limit of these functions. And again, you have this very uncomfortable, very inconvenient fact about Riemann integration, which says that although each Fn's in your sequence are Riemann integrables, the limit, the pointwise limit of this function is not. Something, again, very inconvenient to deal with. That's another reason why Riemann integration needs adjustments, need to be developed into something else, which has more suitable properties for the analysis.